Alright, welcome everybody. In this video today, we are going to discuss what all challenges did Facebook face for scaling its photo storage system and the interesting aspects behind how it is able to achieve the scale that it operates today. So, I want to declutter the information and present in a simple manner from the paper that Facebook has published with the title Finding Needle in a Haystack, Facebook Photo Storage, the link for which will be in the description below. Alright, so jumping into the topic, Facebook, as we know, operates at massive scale. So the massive scale here we talk about in the photo storage system translates to about 65 billion images that it stores. And did you know for each image that people upload to Facebook, it stores about 4 copies of it in different resolutions. And the reason it does is because it wants to vend different images based on the device that the user is using, the network strength, and all such factors. So at the time of writing this paper, Facebook has about 260 billion images in its storage system, and these 260 billion images contribute to about 20 petabyte of data, and the scale at which this system operates is about a billion images per week worldwide, which is about 60 terabytes of data. So what challenges did it face? And before that, we want to understand about the characteristics of this data. So before jumping into any system design, we want to understand what are the read patterns and what are the write patterns of a system. So here we see that Facebook's data characteristics are as follows. It is an image that is written to Facebook is exactly written once, and it is read often because an image can be published to multiple users' timeline, their friends' timeline. It also can be shared as a URL and other stuff. So that's the reason. And an image once uploaded is never modified, which means you can't edit the image after uploading the image. And an image is rarely deleted, so users don't delete the image. So those are the characteristics of the data that we operate with. So before going into the paper, you might wonder why can't we simply use any file storage system? So operating systems are not new, file storage systems are not new. So why this problem is interesting? So before we go into it, let's understand a very basic detail about POSIX file system. Why POSIX? Because it's almost the universal standard of Linux or Unix, which are used in storage systems. Even Mac OS uses is compliant with POSIX file storage system. So if we see how POSIX stores the files, we all know about directories. Directories are what hosts files. So there is a directory. I'm not talking about the directory structure like slash local slash user. No, not that stuff. Every directory has a metadata, and this metadata is what tells which user has permissions to read this file, write this file, execute this file, and when is this created, when is this last updated, all such information. Okay, so that's the very minute detail that we have to know before delving further. So if we know what reasons propelled Facebook to solve this problem or create a system to solve this problem, we would understand this better. So what was the need, the necessity? So this system, the photo storage system, has to perform at scale, which means there should not be any throughput bottlenecks. When we talk about throughput bottlenecks, these are usually like at high traffic rates, degraded user experience due to failing requests and such things. We want high throughput and low latency. We want to serve as many requests as the users are pumping in, and at very low latency. So how much is the latency? We'll talk about it. Then we want to talk about the fault tolerance, which means if something crashes, can I still recover the data? Do I still have it or not? Cost effectiveness, the amount of money it takes to store something and retrieve it. And simplicity. So talking about the first part, when we talk about performance at scale and when we talk about no throughput bottlenecks, so do traditional POSIX file-based systems, do they come with any bottlenecks? Let's explore how an image is loaded when an application says read image. What happens behind the scenes in an operating system and the attached hardware. So when the application says issues a read call to the operating system, then operating system talks to the disk and understands that there needs to be certain amount of memory allocated for reading this image from the disk into the memory, and it retrieves the information of metadata from the inode tables for faster access. Inode tables can be thought of as a caching mechanism, I'd say. So for retrieving the metadata, this inode tables usually store information like the file size, permissions, creation date, all the metadata that we talked earlier. And so yeah, so far we talked about operating system, allocating some sufficient memory here and reading the metadata information from here, and then loading the image, loading the bytes from the disk into contiguous blocks into the memory. And after reading it into memory, it adds a file descriptor of the loaded image, which tells the application, hey, this is the descriptor you got to use to read the file. And it shares with the application, and then application uses the file descriptor to load the image. Now, in languages like Python or Java, when we say depending on application specific things, something dot open as bytes, and in this particular format, a lot of details are hidden, abstracted to the user, and these are the details that are very important to optimize any system, to improve the scalability of any system. What goes behind the scenes at one file read, probably at 100 file reads, probably even at 10,000 file reads on a single system. It may not matter much, but at the scale at which Facebook operates, at any large scale distributed system operates, these minor things do matter a lot. Now, to read one file, how many disk operations are we doing here? We are reading inode tables. These inode tables are also some sort of disk operations. We are locating the file in the disk and loading that into the memory, and yeah, we are doing a lot of operations on the disk, which would eventually cause higher latency, and that becomes the throughput bottleneck of the system. So, to achieve high throughput and low latency, let's define what does high throughput and low latency even mean. So, let's say there is this storage system and there is this service that's vending out the images. Now, if this photo storage system is inefficient, at scale, it would say my throughput capacity has exceeded. I'm taking this much amount of time to process it, but you have been pumping in these many requests, so let me spill over these requests, or I can't process these requests, I'll just throw an exception. So it's a way of throttling, you know. So the photo storage system would, if it is inefficient, would throttle the requests, which would mean the photo storage service that the user is interacting with through the UI will either not respond or respond very, very slowly. Now, this contributes to a very bad user experience. So we can define throughput as how fast can I execute a given request, and how many requests as a result I am able to handle at any given point in time. So that's your throughput. And this is a case where I do not have a CDN and I'm not storing all the images in the CDN. So I just fail to respond to the user, which causes bad user experience, and customers trust obviously on it, which is unintentional, which is not intended, which any large scale distribution system should not aim for. And let's say I'm storing every system. So let's say I upload every image to photo storage, and this image goes to the CDN as a fallback mechanism, and I keep listening to these failures from it, and I always fall back onto the CDN. For example, my photo storage system is still inefficient, it has throughput bottlenecks, and I'm falling back to CDN. At this point, I will be able to serve these requests, but the cost of serving such requests becomes so huge because CDNs do not come cheap. They store by the amount of size of data that you store, so they are expensive if you fall back to the CDN very often. Right, so we defined how high throughput, lack of high throughput can cause issues to the user, how it causes degradation of user experience. Now let's check what is Facebook's approach to solving this problem. So as we saw earlier, falling back to CDN is not a good option. Failing to respond is not a good option. So what Facebook does is, we saw that one read is going into multiple disk operations where it has to read metadata, it has to read the actual disk image. What if I do store the metadata in the memory always, so that I avoid one inode disk operation entirely? What if I'm able to override the system call? So we'll talk about this in detail in the upcoming videos. But for now, assume that if I can somehow reduce the amount of operations that I'm doing when I get a request, obviously I'm taking much shorter time to serve a request, which means I'll be able to serve more requests with the same server capacity that I have, right? So the goal that Facebook took is one read should be at maximum one disk operation only, and keep all the data in main memory so that you don't have to do multiple inode fetch operations, which would cause an increase in latency. If you store everything in memory, you know where to load from in the disk, and that will be like super fast, right? So also, if I store files as small files, I require to store a lot of metadata. If I'm uploading 15 images in one batch, they all belong to probably one post. Can I somehow group them to reduce the size of metadata? Because I have to fit everything in the main memory, right? So if I batch them together, I'll be able to fit it efficiently and read them faster. So that's the idea that Facebook went with to reduce the size of metadata. But all of this we will talk in detail in the upcoming videos. So we talked about two goals so far. What is the third goal Facebook took with this system? So in system design, these become your non-functional requirements: the fault tolerance, the high throughput, the low latency. And your functional requirements usually are ability to serve photos when user requests this, when user updates this. So those become your functional requirements. All right, going through the third aspect of fault tolerance. So Facebook aimed to achieve fault tolerance as a part of this design. Now, what does fault tolerance mean in this case? So let's say I have a data center, and this data center loses power. My data is present in one. If my data is present in only one data center, I won't be able to serve that photo back to the user when they're requesting for it. I won't be able to put them in the timeline of their friends. That's a bad user experience. So if data center loses power, that's a fault, and lack of tolerating it is lack of fault tolerance. We should be able to deal with the cases. Second case is at the scale which Facebook operates, or any large scale system operates, hard disk failures can happen, systems might crash, anything might happen at that scale, right? Even if it's 1 in 1,000, 1 in 10,000, that's still a bad user experience for the affected users. And what if there is a cross country network cable getting cut. It happens more often than you think. So what if there is a network outage to the entire data center? So that also causes a very bad user experience. So we want to avoid all these cases. So even more, so fault tolerance literally translates to tolerating any kind of fault. What does tolerating here mean? Tolerating means the end user not seeing any impact of it. So how do I ensure that there is no impact to the end user even when any catastrophes like this happen? Simply, I do replicate the data across multiple data centers which are geographically distributed, so that even if one data center gets an outage, that it gets caused by environmental factors or any other factor, the other data center is available still for the fallback for me to fetch the data from. So that's the third non-functional requirement. All right, so that's all for today, and see you all in the next video with continuation of this with a lot more technical details about solving this problem. See you.